got here is a concave mirror. So I'm going to have something like this. That's not a good thing to do. Let's put it in the, that's not bad. Let's do that. And the one thing I talked about on Friday, this is Monday, what is today, the 10th?
I think
10th, yeah, okay. So if this is your mirror right here, we'd have like the center of curvature being right about here. So on the very first problem on tonight's homework, you have where it says that the radius of the mirror is 10. Well, if the curvature of the radius is 10, where's the focal point going to be, guys? At 5, because the focal point is going to be half of the curvature. Okay. So what we're going to do is we're going to put a big object, and we're just using an arrow. So I'm going to put a great big object way, way, way over here. Okay. And it's going to be an upright arrow. That way we can tell which way the direction the arrow is going. And then we're going to use all those rules that we wrote at the top of the note-taking page. They're also found on page 609 of your notes. We're going to use all those rules to draw this image. Even though it says draw a ray parallel to the principal axis and then through the focal point on the opposite side, with a mirror, it doesn't go through the opposite side. It actually reflects down through the focal point on this side. So I'm going to draw nice straight lines like I just drew. So this is line number 1. Now, what does it say line number 2 or ray number 2 does? Very good. Number 2 passes straight through the center here, and then, which I drew way, way too close, and then it's going to reflect back on itself. So as it comes down here, it's simply going to reflect right back up. Exactly right. So we're going to draw the third one through the focal point here. And so we're going to go through the focal point here. And then once it hits there, it's going to bounce parallel to the axis. So this is number 3. And the blue one was number 2 here. And then if you notice where all those lines meet, and I should have drew one in a different color, but where all those lines meet, you end up getting this point right here, which I'll highlight it. Exactly right. That's where the image is going to be point. So if all the lines were drawn from the top of the arrow is going to be down here. And so let's look what happens to that arrow. First of all, it's what? It's smaller. It's upside down, or what we call inverted. Okay. And it's real because it's on this side of the mirror as far as it's being projected down. I can actually put a screen there and have it projected on that. Okay, the next one that we're on in our worksheet is where it says page 768, and then it's 23.3. Now, I'm not sure which one Allie's on, but I think she wants to be on that same one. People here. Sam, what is rule number 1 say to do? Okay, a ray parallel. Okay, so I have a focal point and a center of the axis on the right-hand side. That was Brad. Okay, so I'm going to draw a ray parallel to the center axis, so it's going to come across like this. Now, on this mirror here, when it actually hits here, what's the mirror going to do? Yeah, it's going to bounce it up like this, okay? But your eye actually follows that ray back through the focal point like so, okay? So this dotted line is how your eye is going to trace that ray back to. And here's your focal point right there, okay? What's the next step? What's the next thing you do? Let's go to Kelly. Let's draw it. Okay, so we're now going to go to the center of the lens, and it simply bounces back. Well, that was really bad. I'm sorry. Hold on here. That's really, really, really bad. So I'm going to erase that part here in just a second. There you go. That's a little bit better. Okay, so I'm going to take it through the center of the lens, and it simply bounces back on itself. So when it hits here, it simply bounces right back towards your eyeball, and then your eye follows it this way. Yeah, it's so good, Jeff. Uh-huh. All right, so then let's go to the last one, and let's go to voice. Good to have your head up. Hand up, I'm sorry. Hand. Number 3, what do you do then? That's right. So we're going to take a ray through the focal point. So now I'm going to draw it from the focal point up here. Okay. And so it'd come up like this. But when it hits the mirror, it now bounces parallel. It's going to bounce off like this. Okay. So your eye is going to follow it back like this. So I drew it through the focal, shoot Jeff, come on. Drew it through the focal point like this, but your eye followed it back like this. Okay, okay. Hang on here, I know it's a little bit confusing. I drew it from the top of the arrow, right? And I acted like I was going to go through the focal point, okay? But since it hits the mirror, it actually bounces off parallel to the principal axis. But your eye follows it back on this dotted line. So let me get rid of this line here. Okay? Your eye is going to follow it back to here. And this is what makes diverging mirrors or convex mirrors tricky. So if you notice now where all the dotted lines meet is this area right here. And so the image is going to be where? Yeah, behind the mirror, upright and smaller. So once again, now you have a virtual image because it's behind the mirror. It is upright and it's smaller. And this is why on side view mirrors of your car, you have that little note saying objects are closer than they appear because your brain interprets something that is smaller as being farther away. Aha. Very good. So I'm going to do 1 over DO plus 1 over DI equals 1 over F. Very good. Now I got to fill these things in from what's given. So what is the object distance of that first one? Let's go to Samantha. Yeah, what's the object distance? 20 centimeters. So I'm going to put in 1 over 20. I don't know the image distance. That's what I'm going to try to find. So I'll put in 1 over DI. And then the focal length of that particular mirror is what, Chase? Very good. It's a -8 because when something hits the mirror, the focal point's going to be on the back side of the mirror. So it's a -8. So when you hit this mirror here, it bounces off like this. And so since the focal point's on the back, it's a -8. So I'm going to find the common denominator, which is 40. So this ends up being what, Scott, if it's over 40? 2 over 40, because if you multiply the denominator by 2 to get 40, you have to multiply the denominator. And this is going to be 1 over DI. And on the bottom here, I'm going to have a 40. So what's going on top? Hey, Josue? 5. Very good. So Nathan, what's 1 over DI going to end up equaling if you subtract 2 40ths from both sides? -7 over 40. Very good. Then you have to flip it. So DI is going to equal -40 over 7, which ends up giving you somewhere around -16.7-ish. No, I'm sorry. -5.7. Wow, that was good. Yeah, I was looking at the wrong problem. It's -5.71, right? Yeah. Now, since that number is negative, what does that tell you about the distance image? It's behind the mirror, right? So the distance image is going to be behind the mirror. So if it's behind the mirror, do we call that real or virtual? Virtual. Very good. So that simply tells you it's a virtual image. Now we got to do the magnification to see if it's upright and bigger or smaller. This is called the big ball theory. And okay, so the next thing we have to do is figure out the magnification. So if you remember, the magnification either equals high over ho, with ho always being on the bottom, or what we used the other day, we always use the negative di over do. Because if you negative di, that means you live. Very good. So we're going to take this negative image distance we just placed in here, -5.71, put that in there. What was your object distance? Let's go to Nathan. 20. Very good. And so when you put this in here, that's going to end up being a negative. No, it's not. I just screwed up. So where I screwed up was I had to bring down my negative here plus bring up my negative here. So I got 2 negatives there. So it's going to end up being a positive 0.286. So let's talk about what this means. So positive magnification means it's upright. Okay. And since it's less than 1, that means it's smaller. Okay. So now I'm going to the lens notes page, and I'm not even going to write down the 3 rules for array diagrams because they're the same as mirrors. So just go ahead and don't write those down. because they're the same ones on 609 in the conceptual book. This guy is so boring. Golly. All right, let's do the 3 steps again. Let's go back to Bradley with step number 1. You draw a line where? Parallel to principal axis and then through the focal point. So it comes down like this. This is ray number 1. Let's go to ray number 2. Who have I picked on all day? Let's go to, Samantha. So it's going to go straight to the center, something like this. So I'm just going to go straight to the center, and it doesn't move at all. So it's going to come something like this. So this is ray number 2. And so I need to make this one a little bit longer. Okay, so it's going to go down like that. And then I need a ray number 3. What's it going to do, Shelby? Very good. It's going to go through the focal point. And once it, that's the focal point. It missed it, but it's going through it there, okay? And then once it goes through it, it's going to bend and come over here just like this. So this is ray number 3. And therefore, they all meet on the other side of the lens, so I know it's a real image right there. And I'm going to draw that blue arrow. Instead of being right side up, it's going to be upside down, and also one heck of a lot. It's actually supposed to be bigger. Uh-oh. I know it looks the same, but it's supposed to be bigger, all right? So it's going to be big. Big, upside down, or invert it, upside down. Invert it, and big, and what's the other one I'm supposed to answer? Oh, it's real. Go for it. So this is 2 things I sort of use to tell whether an image is real or virtual. If the image is between the lens and the focal point, so in other words, if it was right here, that would be virtual. But in this case, the image is way over here, beyond the focal point, so that means it's real. Plus, I could put a screen right here. I could put a white screen up here and actually have that projected up on there, which is less than 1, it's smaller. So let me go ahead and put these up here real quick. It's 1 over DO plus 1 over DI equals 1 over F. In that particular case, I want you to notice that you have a distance or object distance of 1 over 30. You're trying to figure out your distance image, and your focal length in this case is 1 over 10. So what's going to be the common denominator? 30. I'll go ahead and leave if you know how to do this. So I'm going to put it over 3 over 30 here. That gives you an image distance of 2 over 10. 2 over 30 rather. And so your image distance ends up being 15. Okay, so guys, this is the diverging rays here, or diverging lens rather. And I'd hold off on drawing it as we do this because I guarantee I'm going to screw up. So I'm going to have the diverging lens is sort of concave. In this case, it's both sides. So here's your principal axis going through. And I'm going to use the same rules that I had before. I'm going to put the arrow over here. I'm going to have a focal point right there and a focal point over here. Now, the first step, they said, is to draw a ray parallel to the principal axis. But since this is a diverging lens now, instead of the ray coming down towards the focal point, what's this lens do? It bends it away. So it actually comes up like this. Okay? But when your eye sees it, it's going to follow it back through the focal point. Okay? Everybody sort of got that? Okay, so the next one's going to go straight to the center of the lens, which is somewhere right about in there. Okay, I didn't draw this really, really well. So I'm going to draw a nice straight line through the center of the lens, and it just keeps going straight through. It never gets bent at all. Okay, the next one is really, really tricky because the next one I'm going to draw through the focal point. So I'm going to draw a line that's starting at the top of the arrow, acting like it's going to this focal point here, but since the arrow is going to bend, it's never going to get there. So let me just sort of pretend like I'm coming back here at the top here. Okay, so I'm going to start drawing it from there, like I'm coming towards the focal point. Okay, now if everybody sees this, you see if this line kept going, it would keep going to that focal point. Everybody sort of see that? But the thing is, once it hits that lens, what does the lens do to the ray? It bends it, right? And it diverts it away. So now it's going to go straight parallel with the axis. Okay? And that's what part 3 tells us to do. Now the thing is, though, your eye, if I'm looking at it over here, here's your great big eyeball. Ooh, that's a pretty eye. Look at that big eyeball there. It's got nice little eyelashes, and it's somebody that has big blue eyes. Oh, beautiful blue eyes. Now, your big blue eye is going to follow that ray straight back. Yeah, straight back. That's right, Jeff. That's a straight line. Beautiful. And so what ends up happening is this. All of those rays end up intersecting right at that point. So what's going to happen to the arrow? Say, oh, horseshoes. Daggone it. I was right the first time. It goes straight back. I was doing it the right way. Goes straight back to that point. That's it. That's what I'm looking at. Oh. Okay. So this is what I'm wanting to do right there. Okay. Everybody with me there? Yes, sir, ma'am. So now, if I were to draw that blue arrow to where all those lines intersect, watch what happens now. So now the arrow is what? Smaller. It is. You're right. It's virtual. And it is upright. Now let's talk about why it's virtual. The reason why it's virtual is because since your eye is following these rays back there, your brain is just imagining that it's back there. I couldn't put a piece of paper back there and have all those lines go to that point. Tyler, what's the formula for image distance, please? Well, look it up in your notes real quick. We gave you the other day, or the ones you took today, even. Okay, equals what? Plus what? Thank you so much. Great job, guys. It's a group effort. So if you had an object, Jacob, what would the object distance be? Yeah, but what is it in the problem there? 30. Very good. And what's the focal length of that lens? 10. Now, since it's a concave lens on this very first one, that's a positive 10 because the focal length, as the rays come in over here, they come down to here. So that's a positive focal length. The focal length is positive. If it was over there, that'd be negative. So what I'm going to do is find my common denominator. So I'm going to use 30 as my common denominator for the bell rings here. That gives me 1 over di equals 2 over 30. So your image distance is going to be a positive 15. Okay, so if I want to do the magnification, I'm just going to simply do negative di over dou. Okay. And then what I'm going to do is I'm going to put in the image distance we just found. So this 15 we're going to bring up here. Remember, it's a negative 15 over the object distance, and the object distance was 30. And so what ends up happening is you end up having a negative 0.5. So what the heck does that mean? It means it's smaller, and it is inverted. You got it. Guys, if anybody's interested in medical school and wants to stick around and have any questions for Angela, it's a pretty good, cool person to... Oh my gosh, I'm recording instead of